STAT340 Data Modeling Part 2. So, what is the topic this week? ANOVA. What is this? It's regression with factors. Okay, we talked about regression last week. This is a small extension that we will have to look at first. And the key here is factors. We will come back to that. Then an analysis of variance basics, and this is all about factors. We have to say a few words about the models and assumptions, which is fairly similar to what we saw last week. Hypothesis testing. It's a slightly different machinery, but the idea is the same, but it results in an F-test instead of a T-test. So some difference in the mathematical machinery, but we don't dive very deeply into that. We have to say a few words about parameterizations when it comes to ANOVA, because the output we get differs quite a lot depending if we do, as we say, a reference level modeling or a grand mean reference modeling. So this decides what we actually test in our hypothesis test. So we need to make, there are also other ways than these two, but these two are the ones we will focus on here, how to make contrast, as we say. A few words about pairwise comparisons. This belongs in this part here. And then, of course, since this is the basics, we only look at a single predictor, but what if we have more than one predictor? We will just see how it extends easily, actually, to multiple predictors, this. And then finally a few words about errors and statistical power, which is not linked specifically to ANOVA, but this was the place we decided to put it. Okay, so this is first about the analysis of covariance then, which is just a small extension of last week, so it's still in chapter 10 of the R book. So last week we saw regression, and then we have only numerical variables we learned. So we have a response variable here, and then we have predictor variables. 1, 2, 3, P of them. Could be many. We will see that later. However, all of them are numerical, so there are numbers in all the columns. So with ANOVA, the response variable is still numerical, but predictors may be both numerical and factor. We may add some factor. There should be some numerical here, right? So it shouldn't be only factors, because then we are in an ANOVA situation, as we will see shortly. But imagine you have some numerical ones and then you add a factor. So what is a factor actually? This is important. A factor is a categorical variable where the values are categories. It's not numbers. And this is a big distinction. It's often created from text, but it could also be from integers, but not from decimal numbers, right? Because decimal numbers, then each new value will be a new category. So a categorical variable will typically have the same text in many cells, and then some other text in some other cells, and so on. So some of the rows are sort of belong together because they have the same text, right? And some other rows also belong together because they have the same text, right? And these are the category or levels we talk about, the different texts. So they are ordered, these levels, and that is something we will need to be a little bit careful about. And you should actually decide the factor levels, which ordering they should have, because be aware of this. If you have a text column in a data table, R will automatically convert it to a factor if you use it in a model. And then the levels will be the numerical or the alphabetical order. So if there are text, they will be sorted, you could say, in alphabetical order, so that the level number 1 is the one who comes first in the alphabet. And this may of course not be what you want to be level number 1. So that's why I mention it here. This may not be what you want. You have to make sure that you decide which levels are number 1 and 2 and 3. Especially number 1 is important. We will see. I just mention this because it's something we see all the time. So predictors are both numerical and factor variables. Then we call it an ANOVA situation. Example, birth weights. And you remember this dataset birth? We saw it in the exercises last week. And there we looked at how birth weights of children varies by the weight of the mother. Right? That was a regression analysis from last week. Simple regression. Now we have another variable here, which is smoking, yes or no. This is a factor. This is a factor. Because it has 2 levels. And no is level 1, yes is level 2. And this happens to be the alphabetical order as well. Can you see that? Because N is before Y in the alphabet. But otherwise, this is something we should decide. And the point is that the first level you should think of as sort of a reference. This is the normal situation or default situation, right? While all the other levels are sort of deviations from this normal situation. And okay, in this case, I would say this fits well with saying that no smoking is the normal, that most people don't smoke, right? That's a normal situation, while smoking is sort of the deviation from the normal here. But notice we could reverse this if we want to. There is nothing stopping us in doing that. So you decide what should be level 1 and the rest. So because this has some practical impact on the output. It doesn't really affect the result as such, but the output we get is affected. And as I said, the level 1 category is sort of the reference. Think of it in this way. All other levels are compared against this reference. And as long as we have only 2 levels, there is only one way of comparing. But if we had 3 levels, then we would have both level 2 and 3 are compared against level 1, but not against each other. So this is important when you have 3 or more levels, especially important. So regression with factor. The question, does the child birth weight depend on mother's weight? Yeah, this was what we asked last week. This is the regression problem, question you could say. But now we can also add this. Does this potential relation differ between mothers who smoke or don't smoke? Because now we have this also as a variable here, right? And the model equation, we can write it like this. Instead of using y's and x's, I put in the names of the variables directly. Not so usual perhaps, but then you understand what I'm talking about. The response is still the birth weight, right, of each child. We have an intercept as before, and we have the slope here, right, the effect of mother's weight. This is mother's weight. So this was what we did last week. Now we add, just as another term and another regression coefficient or parameter here, smoking as a categorical variable. And you may think of it as strange that you can sort of add text to numbers like this. Well, it's not really what we do. We behind the scene, R will sort of code this with zeros and ones. But don't think about it. When we specify the model, we do it like this. And the error term is just as before, normal, distributed, with some variance. Same assumptions as with the regression. Constant variance and blah, blah, blah. To answer question A, we simply test, as we did last week, if this slope is 0 or not. This one, right? So that's no difference. Even if we added this term, doesn't change this. To answer question B, we simply test this slope, you could say, but this is not really a slope. Because this one is not numerical anymore, right? So we don't sort of vary along a sort of an x-axis. It has only two values, either yes or no, 0 and 1, true or false, right? But we can see that if this is true, if beta 2 is 0, then this term vanishes completely from the equation. And then this is the same as saying, okay, whether you know the mother is smoking or not, it has no impact on the birth weight. That's what it means. If you eliminate this term, you say smoking has no effect on birth weight, only mother's weight perhaps. So this is exactly what we asked here. Does this relation differ between mothers who smoke or don't smoke? If we reject the null hypothesis, then there is an effect. But if not, we can't claim there is. Note how we fit the full model to all data simultaneously. You don't do it in 2 steps, as you might perhaps think. First sort of fit the model with this, and then fit another model with only this. No, put them in together. And the reason is that, especially when we have interactions, as we will see later, these parameters change whether you fit them alone or together with something else. The estimates you get for beta 1 and beta 2, and the estimates are important for testing this, right? So we can even add more question here. Does the effect of smoking depend on the mother's weight? Or does the effect of mother's weight depend on smoking? Actually, these two are reflections of the same question. Can you see that? And in order to answer this question here, we add a third term. And notice now how we multiply sort of together the two original terms. We put a star here as an indicator of multiplication. And this is what we call an interaction term, where we have two variables sort of multiplied together, because it means that you have an effect of mother's weight here, you have an effect of smoking here, but now we investigate if there is also an effect, or you can put it like this, is the effect of mother's weight depending on whether you smoke or not? Or vice versa, is the effect of smoking depending on your weight, of the mother's weight or not? Right? So this is interaction, when you have this dependencies between the variables. So question 1 and 2 are reflections of each other, and in order to answer, we simply test for this regression coefficient, beta 3. Because again, you can see if this is 0, this term vanishes, and it says there is no effect of smoking depending on the mother's weight, or mother's weight depending on smoking, if this vanishes. So this is how we can now test both the effect of mother's weight, smoking, and if these two have some sort of linkage or dependency. So let's go to an R session and see exactly how we do ANOVA in R. Okay, let's have a look at this birth weight data again. And then I copy this code here into a script here that I have made for week 5. So notice we load the data package and the data set. And here I fit a straightforward regression model like we did last week, just to remind how we did that. Or this was an exercise, I think, last week. So let's actually do that. So I load the package, load the data set, fit the first model, and have a look at the summary of it. Right, so here we have now, yeah, and this is the part we should focus on, right? So we have an intercept, of course, and we have, but it's not so interesting, but we look at the effect of mother's weight on birth weights. So we can see there's a positive slope, and it looks quite significant. It's a 0. It's a sort of 1% p-value approximately, quite small, right? So it's sort of significant. It's a very low R square. I notice here, very low, and that is because I think the relation. So note, even if you have a significant effect, it may not be a big effect. It's a very small effect. So this slope here is in 4.4 watt. I mean, this is the weight of the children, right? And they are in grams. So for each sort of, I think the mother's weights are in kilograms or in pounds, perhaps. We should actually know. I should actually know this. We can have a look at the data set here, or yeah. So the birth weights are in grams, I'm pretty sure. But the mother's weight are probably in pounds. Otherwise, these are really heavy mothers. I think they are in pounds. This is American data, I think. So it means that this summary output that we saw here, for each pound the mother is gaining in weight, the baby's weight gains 4 grams. So it's not very much, right? But it's significant because it's we have a lot of data points here, so it's not random, right? But notice this, effects can be small, but still significant. But then the question is this interesting, right? Nevertheless, let's go to the ANOVA situation. So we fit an alternative model here. And let's ANOVA. Yeah, because this here is ordinary regression, right? So this is the alternative now. We have the same response as before, but in addition to mother's weight, we also add smoking now. So let's do that and have a look at the summary output. And now you can see the effect of mother's weight changed slightly. Can you see that slope here is not the same as before? It's not very different, but it was 4.4, now it's 4.2. So this changed slightly our results, right? But the overall conclusion, I would say, is more or less the same. You can see the p-value is not much bigger, right? It's almost the same, but a slight effect. And then we have this line now. And notice it says SMK yes. So this is so SMK no is now the reference level, and this is now the deviating categorical level, and this is how much the baby's weight changes if you switch from smoking to non-smoking. No, sorry, non-smoking to smoking. Yeah. So since this is negative, notice it's negative. And here comes the order of the levels in. The reference level is not smoking, right? So when you do smoke, the weight of the children goes down with 270 grams, right? Goes down. So if we had coded this the other way with smoking yes as the reference, then you will get the same result but with a plus sign here instead, because then it is the change you go from smoking to non-smoking. Then you add 270 grams instead, right? So you can see it doesn't really change the result, but it changes the output. So when you interpret this negative here, value here, you must know what it means, right? What is it changing from, and what is it changing to? Yeah, sort of small p-value here as well. So I would say it looks like there is a significant effect of smoking. The babies get smaller when the mother is smoking. That's the sort of first conclusion I would draw from this analysis here. Let's make a plot, as we have done so many times before. It's always a good idea to plot both the data and the results, right? So here I just take the fitted model. Again, I add this fitted values as we have seen before. And now I use coloring, the smoking as coloring. And this is nice in ggplot because then ggplot will sort of split the data by this factor, SMK. We will see. So each level will get a different color. So let me make this window a little bit bigger before I run the code. Loading the tidyverse takes some seconds, and here we can see the result. Here we can see the result. So now, since smoking is now a factor, it will, and we used it for coloring, it will pop up here with no and yes. So no is the red, and smokers are the blue, right? And then we can see here the regression lines have both of them have the same slope, right? Because we have only one sort of slope describing the effect of mother's weight, the beta 1, and the beta 2 describes now how we differ between the two categories. And then we can see the children here, the red children you could say from non-smoking mothers, tend to weigh a little bit more than the smoking mothers, but I mean there's still a super big variation in both groups, right? But this is enough to be sort of a significant effect. Then there is a section here about what is actually being done behind the scene. I will not do that here now, but I urge you to have a look at this by yourself. Run this code by yourself, read the text I've written here, so that you really understand what is going on, because it's sort of strange that we fit the model with texts, right, instead of numbers, but it's not really. It is numbers. It's dummy coded, as we say. Let me instead skip down here where we add some interaction. And let me copy this code here. And notice that the second line here will do exactly the same thing. It's just another way of writing stuff. So in this lm function in R, you can write interactions in slightly different ways. So you see the explanation here. But I copy this first one here now. Include interactions. Oops. Yes. And this is how the code looks like. So let me add some space here. So you can see these two terms are the same as before. And then we add this term, SMK colon LW. So this is a way to sort of specify a product in this setting here. Because if you add the star, as you saw here, then it actually means both main effect and interactions. So let's fit this model here like this, and also let's have a summary of it, shouldn't we? And what does this say? Well, again, notice that the slope of the model's weight changed again, and now it's actually bigger. But this is now more difficult to interpret, because now we have this one, the effect of smoking, which is now suddenly positive. What happened here? And everything depends on, or everything is due to this last term here now, because now we have a negative interaction between model's weight and smoking. However, we notice over here that the p-values are now big, so there is no longer an effect of neither smoking or interaction actually. But let's make a plot nevertheless of what happened here, just to understand what it actually means. And this is the code for plotting. So I just, as before, added the fitted value to the model data, you could say, table, model data table, and then I plot and color by smoking as before. And notice now the difference to the previous plot, because now you can see the slopes are not the same anymore. So actually, when you look at the slope here of modest weight, it's not the slope. There are two slopes now. So this is now the slope for the reference case, namely the non-smokers, mothers. This is the smoker. This is the slope of the red curve here, right? And this here is the change in slope when you shift from non-smokers to smokers. And you can see the slope is smaller, so it goes down by 2 point something, right? And you can see it's flatter, right? It's steeper. The red one is steeper, higher slope. So that's why, again, it's super important. And that is also why this one is no longer so interesting in a sense, because this is now the difference between smoking and non-smoking in intercept only, right? And you can see here that the intercept, where this one is 0, it's far out to the left here. It's not really important at all. And that's also why it's suddenly now positive, because if you extend this line here to the far left to where this variable is 0, it is actually lower than if you extend this one to the far left. So this value here is no longer very informative, because it's so outside of the range. It describes the world very far from where our data are. So that's, you could say, that's a problem, you could say, with models where you have interactions, that some of the estimates are more difficult to interpret now. But at least you can see the situation here. But we saw there is no, I mean, adding this interaction was not really significant, so I would conclude that there is no interaction here. The effect of smoking is not different, the effect of mother's weight is not really different between smokers and non-smokers. This is random. The small difference you see here in slope is sort of random. It's not really supported. So I would go back to the previous model and say that this is how much I can say about this data. Okay, again, there is this coding stuff here. I will not go through it. Do it yourself and see if you can get something out of it. So, analysis of variance basics, mostly from chapter 11 in the R book this. And this is the main topic of today. So, what is it, ANOVA? We have seen that with regression models, we always have a numerical response variable. The predictors are typically numerical, but we also saw recently now that we may also have a factor or two in there. When we talk about ANOVA models, the response is still numerical, but now all the predictors are factors. All of them. No numerical predictor variables anymore. And this is typically, I would say, at least my experience is that ANOVA is something we typically use when we have designed experiments. So we do experiments under certain conditions, and that is those are the factor levels. And then we measure some response. So the response is numerical, large or small. But predictors are all sort of factor levels, factors with levels. And there could be many levels, but yeah, I think in most examples we see it's not that many, but more than 2 at least. The fitting of the data, fitting of the model to data. This is exactly the same as for regression. There is actually no difference. And in many ways, there isn't any sort of real mathematical difference between ANOVA and regression. The fact that we replace the numerical variables with factors, it doesn't really change the underlying mathematics at all. So it's the same idea, the least square and blah blah blah. Again, the focus here is on explanation. We want to understand how these various factor variables are important or not important for how the response comes out, large or small. So are there an effect of the predictors on the response? Prediction problems that we mentioned a lot of during when we talked about regression, I would say that this is not typical for ANOVA models. We are not that interested in prediction here, simply because we have all this factor with levels, and it's impossible to sort of extrapolate it outside the existing factor levels. With numerical predictors, right, you can sort of go a little bit outside, or at least in between the observed values of the predictors. This is not possible with factors. If you have a factor with 3 levels, you cannot sort of predict the 4th level. You have no information about it. So explanation is what we focus on. And all the analysis is based on studying the variability in the data, and that's also the reason for calling it analysis of variance. Yeah, we will see that shortly. I just briefly mentioned this app here, but this is something you're going to look at in the exercises. But this is a very nice illustration of ANOVA. So please do the weekly exercises with this one. I strongly recommend. So let's start simple with what we call a one-way ANOVA. And the model equation is very simple, like this. The response is here, and here we have, instead of having sort of an intercept and slope, we now have only heights, you could say. We have the different levels here. So we have an expected value for each level, level number I, right? And we have the error term as before, and that is exactly as before. Expectancy 0, constant variance, because the response here is of the same type as before. So these are the blue parameters now, right? Together with this one. So we have a number of factor levels. I is 1, 2, up to k, right? So for each factor level, we have an expected value here. The number of data cases, that's also in principle variable between the factor levels. So you may have observed the response some number n1 number of times for the first factor level, n2 number of times for the second, and so on. In most of the examples we see here, I think, and in the exercises, we typically have balanced data, as we say, and that means the number of observations is exactly the same for all factor levels. So if you have 10 observations for the first, you also have 10 for the second and 10 for the third and whatever, right? But that is not strictly necessary, right? It can vary. The model assumptions are exactly as with regression. We assume constant variance, independent observations, normal distributed, and so on. Error terms, constant variance, independent data cases. That's the assumptions typically. The hypothesis testing that we typically start out with is this. Is there any effect of the factor as a total on the response? So the null hypothesis is actually this rather special one here, saying that the expected value for the first factor level equals the one for the second factor level equals the last factor level. So all are the same, right? It's not like one is 0 or something. We only the null hypothesis is that they are all identical. meaning that it doesn't matter if you shift from one factor level to another, the response is the same. And this corresponds to when we in the regression setting we tested if the slope was 0, right? And here is no slope, but if there is no effect of moving from one factor level to another, it's the same as no increase or decrease, right? It stays constant. So this is the null hypothesis. And then the alternative, at least 2 of the levels differ. And notice this, that we don't really say which one. We only test, are they all identical, or is there some factor level that deviates from some other? I shouldn't say not the factor levels, but the response, right? Is the response due because these mu's here are the response, right? This is not the factor levels themselves. There is one mu for the first factor level, another one for the second factor level, and so on. Okay, so here we can sort of think of how would the data look like. If the null hypothesis is true, it would look something like this. So here we have the 3 factor levels, right? 1, 2, and 3. And here we have the response, the y. And then we see if we measure the response on the first factor level, it comes out on average here with some variation, right? And the second one here and the third one here. And of course, since it's random data, it's not exactly the same, but these are not significantly different from each other, right? Because they are more or less at the same level, and especially if you consider the variation. This is the case where the null hypothesis is not true, where H1 is true instead. Because here we can see, okay, factor level 1 and 2, they are quite similar, but factor level 3 clearly deviates, right? We can see the response here is much bigger compared to under these 2 levels. So this is a situation where we have an effect of something, and in this case we can see it was factor level 3 here. Okay, the estimates, so each of these mu's are estimated by the mean for that level. That's the least squares solution actually. So if you have data for level 1, 2 and 3, the estimates of these mu's are simply the average for all the 3 levels, for each of them, right? So mu I hat is simply the average of the response for that factor level. And then we write it like this, yi dot, and this dot is then mean average over all j's in that factor level. So that's quite typical to write it with a dot here. We can compute the variability as sums of squares, and we have done that before, right? The total variation in y is this one. So you take all the y's and you subtract the grand mean, as we call it, and then it's y dot dot, right? Because this is the average over all response variables, regardless of factor level. So you take the observations one by one, minus this, square it, and then add this up over all values of j and all values of I. Total SSY. This can always be split into 2 components. The first one, 2 components. The first one is the variation between the factor levels. And that can be, I call it SSA here. And here you have the mean inside each factor level minus the grand mean. And then you sum this for all the factor levels and overall, within each factor level and overall factor level. The variation in y within each level, that's the other source of variation in this total here. And that's what we write here. So we have within the factor level the observations minus the mean here, right? The same as you saw over here. So you sort of split the variation into two steps, you could say, or yeah, two sources, SSE, SSA. And then when we do the hypothesis testing, we divide this sum of squares by the degrees of freedom to get what we call the mean square error for A, SSA here, and the similar mean square error for this SSE here. And these are if the null hypothesis is true, then these should be more or less the same. So whether you look at sort of the between level or within level, it shouldn't be any difference. And if you go back to the previous slide, it's sort of intuitive, right? That if there is no effect of factor levels, whether you compare within or between them, it's sort of the same variation. So if this alternative is true, at least one of them differ, then this one here should be much bigger than the second one. Then the variation between the factor levels should be bigger. And this gives us now the F test here, which is then this ratio actually. This one divided by this one. So we see that if the null hypothesis is sort of true, it should come out around 1. If the H1 is sort of true, it should be bigger than 1, right? So when null hypothesis is true, this is F distributed with k minus 1 and k times n minus 1 degrees of freedom. And the F distribution is just like a T distribution. It's sort of can be derived from the normal distribution. So if the data were not normal, you can do exactly these computations here still, but this one will no longer be true. That this F value, if you compute it like this will no longer be F distributed if the raw data were not normal distributed from the beginning. So then we reject the null hypothesis if F is large, just as we did with the T distribution. But the F distribution looked very different from the T distribution, because the T distribution is sort of bell-shaped, almost like the normal. F distribution is very far from it. And we can see the value 1 here, right? So in order to have a small p-value now, and that's the shaded area here, you have to have a big F value, right? Bigger than 1, and much bigger than 1 actually. And this depends on this degrees of freedom here that alters the shape of the distribution slightly though. But again, it's the shaded region. So if you get an F value of, like, let's say 3.5, that's sort of what we have marked here. If the F is 3, this one here is 3.5 times bigger than this one, then you can see the p-value is pretty small, and then we can reject the null. This could never happen if this was true, right? Or very unlikely. This is the probability, right? The p-value. Okay, let's see how we do a simple ANOVA in R. So let's have a look at ANOVA basics in R. And before we do the actual computations, let's load the dataset here. So, ANOVA basics. But so let me just clean from earlier here and run this. Yields unstacked. What kind of data is this? And this is not too uncommon to see, and this is really data in a bad format. So before we actually start to do some computations, we need to store this in a proper way. And what you can see here, we have typically, this is a factor, right? The title of each column are 3 soil types. And the response for each soil type is stored as columns here, right? But this is not how you should store such data. You should store all the response values in one single column, the Y column, right? And then you should have another column which is a factor with these as texts inside the column, right? Not as column names like this. So let's first do this rearrangement or data wrangling that is required here, I would say. So let's. I want to show you this because I see often data in the wrong format, and if your data is in the wrong format, it's the first sort of obstacle in data analysis. So first, let me load the tidyverse packages here, and I create now a new data frame that I call yields, which is not unstacked but stacked, and that's the whole point, stacking your data. This is one function for doing it. It's part of the tidyverse. There are some other functions in R, but I like this one. And what do we actually do? We take as input the original data table. We say which columns do we want to stack. And everything means all columns, because we want to put these three columns on top of each other, right, into one long column, stacking it. And then we say that what is now column names should be made into a new column called soil type. And the values that we now stack should be into a new column called yield. So let's run this like this, and then we can look at the first rows of the table. And now it's in a tidy format, soil type and yield. And we can even click it open here in the viewer. So now you can see all the soil type information is here as a factor with 3 levels, either sand, clay or loam. And here we have the yield. So these are actually data for some field crops grown on 3 different types of soil. So that's the factor levels. And this is the response, the amount of crops that you harvested, right? So we will now see if there is an effect of where they were grown on the soil type, right, on the response. So this will be our response, and this is the predictor. Yeah, and here, let me copy this code as well. So what I do here is, mentioned this earlier, that whenever you have a factor column like we have here, and it's all right now it's a character, it's filled with text, it's not really a factor. And then if we let R sort of transform this into a factor, it will sort the levels in alphabetical order. So clay will be the first level because C comes before L, which will then be loam will be the second level, and sand will be the third. So clay will be sort of the reference. But this may not be what we want to have. This may not be the way we want it, right? We may want to have one of these others as a reference. So here I show how you sort of create this into a factor manually. You take the yields table that we created above here, and we mutate the soil type column and say the soil type should be a factor based on the original soil type, which is text, and here are the levels. And now you can see I decide this should be the first level. But if I want any of the others, I just put some of the others here as the first level. And the first level is the important one, the reference level. The others, after that, it's not important which order they are. Which one is first? So if I do like this, and we can use this summary function that we have seen before, we now have soil type as a factor. 30 data cases, and if we scroll to the right, we can see it's balanced because it's exactly 10 clay, 10 loam, and 10 sand. So this is a nice data set now. We can also plot, and we should actually always plot data, right? We have learned that. Always plot data before you do analysis, to see if there is something strange at least. And how do we plot data like this? Well, the box plot is typically what we use now, where we then have, as on the x-axis, the factor and the yield as a y-axis, right? So let me just run this so we can get a plot here. And now we see the data very nicely, right? We see the soil types, clay, loam, and sand. And here is the response. And okay, it's not so easy to tell from this plot if is there an effect of soil type. Well, yeah, we can see that it seems to be biggest harvest here on the loam and smallest on sand. So perhaps between these two there is a significant difference. But this one is surely in the middle, clay, right? Now we can do the ANOVA. And here is the code for fitting the model, and you can see it's still the LM function. And it's not different from what we saw when we did regression. You specify the response here as some numerical variable, and then a factor here. And the data, where is the data, and so on. So we can just fit this object here. And now, in order to do this testing of this null hypothesis here, right, that we saw, all the expected value for all factor levels should be the same. If that's the null hypothesis we want to test, we have this function called ANOVA that we can use for that. ANOVA of this LM object. So if we run that like this, we get an output up here. And here we get then the F value. So soil type factor, we can see the sum of squares, right? And here is the F value. Here is the F value. So here, so this is the residual sum of square. Yeah, here we have the mean. Here the mean squares, right? The MSA and the MSE. So here you can see this is much bigger than this one. So the F value comes out 4.2, and this is quite small. Yeah, 2%, 2.5%. So it's sort of significant, I would say. At the 5% level, there is some differences here between at least two factor levels. And from the plot, we can see that that must be between these two, right? Loam and sand. Of course, we can also plot the LM object to get some diagnostics, like we did for the regression model. So here we can see the residual versus the fitted values. So this will then be mu1, mu2, and mu3, or mu, I should call them mu sand, mu loam, and mu clay. And we can see the residuals pretty nice. This is pretty nice, right? Fairly constant variance and so on. Normality, yeah, this is pretty nice. So this is this is fine. We recognize the same diagnostic plots. So the effects that we see in ANOVA versus regression. So remember when we did the regression modeling, the effects of a predictor means the slope is not zero, the corresponding slope, you could say. If there are multiple predictors, there is one slope for each of them. So we tested if this is zero or not. When it comes to ANOVA, there are no slopes, because we now have one parameter for each level of the factor, and the F-test that we just now saw tests if there is an effect of including the factor with all its levels in the model, right? So remember this clay, loam, and sand example that we just looked at. So there is no slope, but the corresponding sort of effect of having a slope is that there is a change when you move from one factor level to another. But it's not a line, it's not a curve, right? Because there's nothing in between the factor levels. either here or here or here. So how should we actually test if there is an effect of factor level? For instance, is this a meaningful null hypothesis? Mu I, that's the expected value for factor level I, equals 0. No, I mean this doesn't make sense, right? Because whether the yield is 0 or not, that's not what we are asking about, right? The response value here, 0 is not a special value here. 0 could very well be one of the observed values, right? And whether it's 0 or not doesn't tell us anything about effects. The effects is if we want to actually compare the expected value for each factor level to some reference. Is there a change, right? Is there a change between the factor levels or between some reference and the factor levels? Or compare them directly to each other. That's more meaningful, right? It doesn't really make sense to test if the response is a certain value or not. And then we have to say a few words about parametrizations and contrasts, because this inflicts the output we get. So there are two ways of doing it. There are more, but there are two ways we will discuss here in this course. The first one is to use one of the factor levels as a sort of a reference level, and I mentioned this before. So we actually want to compare the effects by comparing how the response is at the other factor levels compared to this reference level. And in R, you can set this by using the options function and specifying contrast equal this one, counter treatment. That, ignore the second one here, this is something else. It's the first one that's important, because this tells now R to do ANOVA with one factor level as the reference, and that's always the first factor level, which is the treatment, which is sort of the reference treatment, you could say. And this is meaningful if one of the factor levels is sort of the normal situation or default situation. And this should then be the first factor level. Then we typically write the model equations slightly different, like this. The response is here again, right? I for each one for each factor level, J one for each observation inside the factor levels. And notice we now have a parameter mu here. This is a blue parameter, right? And this is sort of without any index, plus, and then we have some alphas here. And there is one for each factor level, I. And then we have the error term as before. So I is 1 to k, j 1 to n, and then the first factor level is always 0 here. The alpha 1 is always 0. And how should we interpret this? It means that this is actually the reference. This is the response reference, response at the reference level, which is level number 1. So this one is 0 because we add nothing, right? For if I equals 1. But for all the other factor levels, the alphas may be different from 0, both positive or negative, right? Depending on if the response changes in positive or negative direction when you move from the reference to some of the other factor levels. So when you do this, when you use the lm function in R, as we will see shortly, the output, if you have this way of contrast, the first level is always the reference. So the estimate of the response under the first level is this one, the estimate of this one. And then the other levels are simply this one plus the estimates of the others. There should have been a mu hat here as well, actually. You can see now. There should have been this should be the same, right? Because the estimate of this one, we need the estimate up here first, and then we add. So all the sort of effects of the additional levels are given as deviations from the reference. We will see that. So again, I said this 100 times before, level 1 should always be the sort of reference level in this case here, when you use counter treatment. Okay, the other choice we have, instead of having as one of the levels as a reference, we can use what we call the grand mean as the reference. And what is the grand mean? It's simply the average of the response across all levels. Right? That's the grand mean. So none of the levels are special, but the average of everything is the reference that we compare against. So each factor, the response under each factor level is then compared to this grand mean. And if you want this type of comparisons, you set the same options to counter sum instead of counter treatment. And again, if you write the model equation actually in exactly the same format with the same indexes, but with this restriction now. The sum of all the alphas is 0. And that is because this is sort of the grand mean now, right? The mu. And then all the deviations, whether they are positive or negative, if you add them up, they must add to 0. Some of them positive, some are negative. Otherwise, this would not have been the grand mean, right? So this must now be fulfilled. So remember in the previous case, it was the first level that was 0. Now we say sum of all levels is 0. And R will now output the grand mean as sort of the reference, and then the deviations from the grand mean for the, and notice, not for all the factor levels, but for the k-1 first of them, but not the last one. And that is because since this must be fulfilled, right? Once you have all the first k-1 values, you also have the last one, because we know it sums to 1, so the last one must be the negative, or the sum of all the previous negative, for this to be true, right? So for that reason, the last effect is never output. You have to sort of compute it manually if you want to know its value. So estimates for the original levels will now become, for level I, the response for level I is now the grand mean plus this deviation. And then notice you have to compute the last one yourself from all the other ones. Okay, so these were two ways of contrasting. But instead of testing effects versus some reference, whether it's one of the levels or it's the grand mean, it's still sort of a reference. We may instead want to test if there are differences between all the levels. So for instance, in that soil type example, is the yield for clay significantly different from the yield from sand, or clay versus loam, or loam versus sand? It's not so unnatural to think of this, right? And this we can also do. We will do this. Notice, however, if you have now k factors, k factor levels, there will be k times k-1/2 pairs. So this can be very many tests, right? And especially if you have multiple factors in addition, this becomes really, really horrible. So this is something you can do for, I would say, for a smallish type of problem. You can do this. But if you have a big model, in the sense you have many levels and also many factors with many levels, then it's really, really horrible. We will see some examples where we start to see some of this. But it's still a possibility. What we actually do when we do this many tests, because this will be many tests, right? One for each pair. Since we always have a sort of p-value threshold, right? Let's say we have it at 5% rejection level. Then we will, on average, 5% of the test, we will claim significance even if there isn't any significance. So this is sort of the error tolerance, right? It means you make some errors. Not often, but some. The point is that when you make many tests, even 5% of a very large value is quite an amount, right? So that motivates us to be slightly stricter than we would otherwise be. You can, of course, just lower the threshold, but what we typically do is to make some kind of correction to this computed p-value. So the p-value is actually interpreted as before, but it's not actually the same p-value as you used to see. And what we will do here now when it comes to ANOVA and multiple pairwise testing, we would use what is called the Tukey correction. And I will not dig into this, simply because there are many other ways of doing this, and I don't think it's worth it to sort of dig into all of them or many of them. So just accept that this is sort of the p-values you now get are sort of corrected in the sense that they are sort of stricter in the you can still reject at the 5% level, but it's harder to get small p-values with this Tukey correction. Okay, so let's go back to R and see how we can do this comparison either against reference or all the pairwise. So parameterizations in R. So let's continue with this soil type example, and let me copy this code here to see how we can use one of the factor levels as reference. So from the lecture slides, you saw this is the way you specify how you make the comparisons in an ANOVA. And I should say that this is actually the default. If you do not change anything, this is what you get. The contrast treatment way of comparison. But let's run this now, like that. And then we fit the LM object again with yield as a response and soil type as predictor. Same as we saw before. And now, instead of using this ANOVA function that we used up here, we now use the good old summary function that we have seen multiple times before. And then we get an output that is also somehow similar to what we have seen before. Let me delete this. So, you may recognize most of it, right? But notice now what we are given as output. First, we have an intercept here. And what is an intercept here now? Well, the intercept is reference level, the response for the reference level, and this is level number 1, right, in our factor. And now we have to know how the factors are ordered now, right, to really understand it. But we can actually see it because so this is 11.5, right? That's the average yield if you are growing on clay, because I happen to know that clay is the reference level. That's level number 1. And then we see for soil type loam, the estimate is 2.8. And this is not now the full response for 2.8. This is the deviation from the reference, right? So actually the expected value for loam is 11.5 plus 2.8. That's how much you change when you go from the reference clay to the loam. You add 2.8, so you get more yield. And same if you go to soil type sand, it's negative, minus 1.6. So this one minus 1.6 is the expected yield for sand. And if you remember the plot, I just deleted them. We saw that clay was sort of in between the other two. So this makes sense. This is the contrast treatment, right? You test, you set one of the levels as reference, and then you estimate the deviations. When you go from the reference, you change from the reference level to some other. Let's see the other option we have, the grand mean, and it's not very different. Then we set options again, but now with counter sum instead of counter treatment, and we do the exact same model fitting, same model specification, like this, and the same summary. But now it looks slightly different, because now the intercept is not the average for any of the levels, it's the average for all the levels. And that's 11.9, right? It's not 11.5. It's 11.9. That's the average across all levels. And now you see soil type 1. It doesn't say soil type clay, but I happen to know that level number 1 is clay. So this, I don't know why it doesn't output the name of the level here. This is peculiar to me, but that's how this function behaves. And then we can see the deviation is now minus 0.4. So this is now, when you go from the grand mean to the first factor level, it goes down by 0.4, right? When you go to the second factor level, it goes up by 2.4. And notice the third one is not listed. And in order to see how the expected output would be for, or the expected yield then for the third level, you have to take minus this one, and add to this one. So it will be the third value like that. It only outputs the two first, because this plus this one plus the one we don't see should all three add to 0. So it means that the one we don't see is 0 minus this one minus this one. Okay, so you can see it's not very difficult, and the p-values are interpreted as before, right? There is no difference, right? So here we have, yeah, okay, if you use 8% rejection level, it's significantly different. Loam is significantly different from clay then, right? But not sand. But this was also very weak, right? And here we can see, yeah, the last one here is sort of, no, the second one here is significantly different at 5% level from the grand mean. And it's positive, right? So it's more than the grand mean. And we don't see the last one, and that's a little bit unfortunate. But if you really wanted to test the last one against the grand mean, how can you do that? Well, you can actually just go in here, change the order of the factor levels, and do it again, so that some of the other ones is the last factor level. So that's a way to sort of cheat your way. It's sort of strange that you don't get the third output, I have to say. Let's see how we can do all the pairwise tests. No, sorry. Yeah. Yeah, okay. You can do this here if you want to. That's what I said. If you can rearrange the factor levels, right? And do the same again to see if you have a significant effect. Look at this code if you want. Let's do the pairwise testing instead. Let me copy this code. All pairwise tests. So instead of testing against some reference, we test the effect of the levels against each other. And then here we use a function from this package, R package, mixlm. So install this first. And the function is called simple glht. And then you see you have to have fitted this model first, and you have to specify which factor do you want to do the pairwise testing for. And of course here there is only one factor, so it's the soil type, right? The correction method, how to correct the p-values, Tukey. And that's what we stick to in this course. And now we also have to specify a sort of confidence level instead of a rejection level. So if you want to test at the 5% level, you specify 0.95 here, 95%. Right? So let's run this and see if it makes sensible output. Load the package, do all the pairwise testing, and then we print it. And what does it output to us? Yeah, it outputs the confidence intervals. So here we now have the test of clay versus loam. And here you have now the lower limit of the confidence interval, and here you have the upper limit of the confidence interval. And notice now it makes sense to to see if 0 is inside this interval. Because if 0 is inside this interval, it means there is not a significant difference between the responses of these two factor levels. And this one includes 0. Can you see that? Because it goes from a negative value at the lower end to a positive value at the upper end. So this one includes 0, and there is not a significant difference between them. If you compare clay to sand, the same thing seems to be the case. The lower value is negative, the upper value is positive, and also we can see the p-value. But here we have a significant effect between loam and sand, because here we see the lower value is positive, and then the upper value is of course even more positive. And here we now have a p-value less than 5%. So if a 95% confidence interval does not cover 0, it's the same as having a significant effect at the 5% level. Yeah, it's also possible to plot it. I'm not sure if it works. It doesn't work. Yeah, it worked now. It has some problems, this plotting here, but we have all the information we need from this, right? But you can see it graphically here instead. Clay versus loam, you can see the confidence intervals plotted, and you can see the first one covers 0. 0 is marked as a sort of the magical value here. Second one covers 0, but not the third. So here we have a significant effect then. Loam against sand. The yield we get is significantly different between these two soil types. So before we completely finish with the parametrizations, let's just revisit this hypothesis testing again. Because from the previous R session now, we saw this output here, right? We had, and this was for the first parametrization with a reference level, right? So we have an intercept, which is level number 1, the expected value on the level 1. And then we saw the deviations moving from level 1, which was clay, to level 2 or to level 3. And notice over here that it's t-values. This is not an f-test, right? Because, and what are actually the null hypotheses now? And this is super important, I would say. This is one of my sort of big issues in STAT340, I would say, that whenever you see a p-value or whenever you present a p-value to someone, you should be able to say what was the null hypothesis. If you reject the null hypothesis because you have a small p-value, you should know what is the null hypothesis that you are rejecting. That is sort of the minimum requirement. Because I see p-values all over the place when I read articles, and I'm not sure that the authors are always aware of what they actually mean. So let's stop and see here. What are the p-values? We can see the p-values. What are the null hypotheses? Remember this way of writing the model now, right? Where we have the response, we have sort of a reference here, mu, either it's one of the levels, factor levels, or it is the gram mean, but it's still a reference, right? And then we have the deviations from the reference for the various factor levels, right? So the null hypothesis, there are actually several of them, right? One for each factor level here now. The deviation is 0. That's the null hypothesis now, right? Because if there is no deviation, it means that all of them, the response is the same regardless of factor level. So there is one null hypothesis for each factor level saying that the deviation for the factor level is 0. And this is different from saying that mu equals 0, right? And this is very much similar to what we did in the regression setting where we had the slope. We tested if the slope was 0, and this is exactly the same thing, but in the context of factor levels instead, right? So jumping from one factor level to another has no effect on the response. That's the null hypothesis. And with this counter treatment, this index I is from 2 to k, right? Because level 1 is what we test against, right? It's the deviation from. This is now the response on the level 1. So and this is exactly what you see over here, right? So we can test if there is an effect of changing to one of the others who are not reference. And the null hypothesis says no deviation from the reference level if the null hypothesis is true. With this counter sum setting, grand mean, then notice I goes from 1 to k minus 1, right? Remember from the previous R session, we saw that the last factor level is never output. But if you go back to my go back to my lecture document, the HTML document, I had a small session there of how you can just sort of reorder the factor levels to get a similar test for the last one as well. So it's possible to test for all factor levels actually. But then you test against the grand mean, right? Is there a deviation from the grand mean? And that is not the same as over here, right? So you could, in principle, have an effect which is significant in one of these cases, but not in the other. So it depends on your, it's not just to say I have a small p-value. You have to, first of all, you have to know how did you test, right? Was it with a counter treatment or counter sum? And what does it mean to have a small p-value? Right? It's a lack of effect of something, but effect of what compared to what? This is super important. You should be able to control this now, right? Don't present p-values unless you know what they mean. So, and note the t-test here. It's a t-test because this is exactly parallel to what we did with regression earlier. And actually the computations are also actually the same then, leading to a t distribution instead of an f distribution. Because now we can sort of estimate here, right? Divide by the standard error for this estimate, and then you have a t distribution with a certain number of degrees of freedom. And that is exactly what you see here. So this was fairly parallel to what we did with regression. More than one factor. So how about if we have two factors or even more? But let's consider two factors in our model. And this is possible, no problem. Once we have two factors, we may also include what we call an interaction term. And please note, it's not that you have to do that. But once you have two or more factors, at least you can include an interaction term. And I will do that here now just to show this. So here is the model equation if you have two factors and an interaction term. So notice the response. It has now 3 indexes. We have the reference or whatever you call it as before. Here we have the first factor with its levels, deviations from the reference, right? As we have seen before. And here is the second one. No different from the first one, except of course the different name. I call them alpha and beta just to keep them apart. Here is the interaction term. And I have to say 2 words about the name it has gotten. This is how it's often written, but you should consider this parenthesis here to be one symbol. We could just as well have chosen to call this with a third Greek letter, because this is a factor just like the others, right? With its levels. But the reason we call it like this, parenthesis alpha beta, is that it emphasizes that this factor is just a combination of the 2 other factors. But think of it as a single symbol. And also notice the indexes are the combination of the indexes over here. So if this has 2 levels and this has 3 levels, then this has 2 times 3 equals 6 levels. Yeah. And here is the error term as before. And of course, assume we have small a levels of the first factor, small b levels of the second factor, then we have small a times small b levels of this factor, and k is now the numeration of the repetitions we have within each combination. So for each combination of alpha and beta, we have n observations now. That's the k. Okay, how about the parametrizations now, the contrast? It's actually quite similar to if we had one factor, but of course it's sort of more complicated with because it's more to sort of more symbols. But again, if you use the reference level parameterization, the first level of alpha is considered to be the a reference level, and this first level of beta. And notice here that for all values of j or all values of I, this equals 0 as well. So there are actually multiple sort of reference levels for the interaction term. So it means that the response you estimate with this one is the case where alpha, where you are in the first level of alpha, first level of beta, and in either one of these levels here of the interaction. Okay, the grand mean, exactly parallel to what we saw before. The sum of all the effects of alpha must sum to 0. Same, the sum over all levels of beta must sum to 0, deviations. And also here, if you sum over all values of I of this or sum over all values of j, it should also sum to 0. So these are the requirements now, or yeah, parameterization. A full factorial design, that's something you hear from time to time. What does it mean? It means you have data for all the combinations of all the factor levels. And this is sort of the best type of data you can have. All levels of alpha combined with all levels of beta. And if you then, in addition, have a balanced data set, it means that for each of these combinations, you have exactly n observations. That's sort of the perfect data set, you could say, for testing or revealing all the effects. Both the main effects, we call these main effects, and these are the interaction effects. So for revealing both main and interaction effects, a full factorial design, balanced full factorial, is sort of the optimal data set. It's not always possible to do that, right? For practical reasons. I mean, if you have many factors with many levels, it's really many combinations. So it may be expensive to conduct experiments of all these combinations, right? And sometimes for other practical reasons, it's not possible either. then you have to do something else. And if you want to study more about experimental design, we have a course specifically for that, the STAT340. So we will not dig much into that, or we will not dig at all into it here in STAT340. I just mentioned it briefly here. Let's have a look at the hypothesis testing. So let's consider this null hypothesis again, namely that all the deviations for the factor alpha is 0. This is the same as saying there is no effect of factor alpha at all, right? Because regardless of level, there is the same the response is the same. That's what this null hypothesis says. Or we can have the other null hypothesis here saying the same about factor beta. So these are main effects, right? Main effects of alpha, there is no, regardless of which level you choose, the response will be the same. Main effect of beta, regardless of which level you choose, the response come out the same. There is no effect of beta either. Or you can test the interaction. The null hypothesis for the interaction is again that all of them are 0, right? So these are the sort of the three main null hypothesis you can put up, and the first thing you should do really, because if you cannot reject any of these through, or if some of this is not rejected, then you can sort of throw out that factor, right? If this is rejected, you can forget about factor A. If this is rejected, you can forget about factor B. And if this is rejected, you can forget about the interaction. Throw it out of the picture altogether. So again, we split the total variation in the response into components, just like we saw before. But since we now have two factors and also an interaction, we have both SSA for the alpha factor, SSB for the beta, and SSAB for the interaction before we have the SSR. If you remember earlier, we had only this SSA and SSE. So this this complicates the picture slightly, but it's the same principle, right? You sum all squares, sum all squares. And then again, we divide by the degrees of freedom for each component, and that is this one where capital N is actually the total number of observations, because we have A levels of factor A alpha and B of factor beta. So we have this many combinations, and then we have N observations for each combination again. So we have this full balanced full factorial. Okay, so if you take this one then and divide by this one, you get the MSA. If you take this one and divide by this one, you get the MSB. And if you take this one and divide by this product, you get MSAB. And we compute F statistics as before. And here I do it for the first one. So MSA divided by MSE. Remember we saw this before? And here you see the formula, right? You take the SSA divided by the degrees of freedom. This one divided by this one. And the numerator is this one each time. So, and if you want, so this gives you one F value, right? For testing this null hypothesis. In order to test this null hypothesis, you just replace the numerator here. MSA, replace it with MSB, which would then be this one divided by this one. But the denominator should be the same. It's always this one. Or with the interaction, to test this null hypothesis, you take this one divided by this product here as the numerator. I get the third F value. So there will be 3 F tests here now, one for each of these. Okay, let's go to an R session and have a look. So let us consider this weights dataset, a new dataset here. So let me just copy this code here and add it to my script. Yeah, well away from the rest. So the weights dataset, and let's look at the table. It has 3 columns, and it's actually about weight gain based on some diets with some additional supplements. So you can see the response is the gain in weight for the different persons, I suppose. diet is a factor, and we can see it has three levels: barley, oats, and wheat. These are plants actually, but I guess the diet is based on these plants then. Barley, oats, and wheat. Right? And supplement is also a factor, and this has four levels: Agrimore, control, soup again, and some. Is no room for the name here, but sorry, I should actually have. The first thing I notice here, there is a level here called control, but this seems to be level number 2, right? Because it's sorted alphabetically. Agrimore, comes before control in alphabet. This would be a natural level 1, I would say. If I was going to use this reference level contrast, I would have this as the reference, the control, right? So that's the first thing I want to change now, just to show you how to change this. So this code here, I add now just to change that. So notice I take the data frame, pipe it into the mutate function, because mutate allows you to change the content of a column. And it's the supplement column that I want to change. And I want to turn it into a factor. I mean, it's already a factor, but now I sort of return it into a factor again based on the existing column. So it doesn't really change the content, but I now specify the levels and the ordering. And now I put control as the first level. And then I keep the other one. It doesn't really matter how I order the rest. The important one is which one is level 1. So please note this, how I did. And then, of course, I store the result into a new version of the same table. So here I take the old version, I do something to it, and I store it as a new version of the table. Let me run this code. And then we can actually run the summary viewing again. And now you can see control has been shuffled so that this is now the first level. Okay, this was data wrangling. We can also have a look at how many observations do we have for each combination. How do you do that? This is a quick and easy way to do it. Because I know that one of the factors is called diet and the other factor is called supplement, 2 factors. Then I use this table function. So if you go over here and look at, yeah, let me run it again because the window was a little bit like this. So we can see that this is perfectly balanced factorial design, because for each level of diet down here and each level of supplement, which is over here, we have observations for all combinations, and we have also exactly the same number of observations for all combinations. This is super nice. So let's also make a plot of the data. And how should we actually plot data like this? Here is one way of doing it. We will see another way shortly. I like to use the ggplot, right? And then I use the box plot, as we typically do when we have factors. But since I have 2 factors, I now have to choose one of the factors to put on the x-axis here, because the y-axis must be the response. That's always the case, right? The y-axis should always be the response. And then I'll put one factor as an x-axis here, but what about the other factor? Well, I use what we call faceting, which means you split the plot into multiple panels. And now I use the second factor for splitting into multiple panels. So let me run this and show you. You will understand when you see it. This is how it looks like. So notice now on the x-axis we have the 3 levels of the diet factor, right? Barley, oats, wheat. Barley, oats, wheat. Barley, oats, wheat. Barley, oats. Same for all. but we have 4 panels, and that is one for each of the supplement levels. The control level first, Agrimore second, super gain third, and super sup fourth. And on the y-axis we have this gain in weight. And now we can actually see right away how the data distributes over this, right? We see clearly that barley gives the highest gain in weight in all 4 cases. Can you see that? Barley is on top in all 4 cases. Oats is in the middle in all 4 cases, and wheat is at the bottom in all 4 cases. So the picture you see in one here is more or less the same you see in all the other 4, right? This is important. This is not always the case, but this is how it is now. So let's fit a linear model here and run this ANOVA test. Like that. So I use this contrast treatment again, right? And actually, yeah, let me do that. And then I fit the model with diet as a factor, supplement as a factor, and the interaction. This is how you specify that. Like this. And then we can do this ANOVA, testing this null hypothesis, these 3 sort of main null hypothesis that we first should always test, because this tells us if there is some effect at all of some of the factors and interactions. And here we have the result. And then we see for diet, the p-value is super small. There is clearly an effect of diet. And I mean, when you see this plot here, it's not surprising. We can see that there is a very big difference between the 3 diets all over the place. So this matches our intuition now based on the plot. What about the supplement? Yes, it's also highly significant, super small. Power of 10 to the power of -7, right? -7 here, and this was -14, so this was extremely small. But again, and this was perhaps not so obvious from the plot, that this is also, it means that the level here, you can probably see that when you go from control to Agrimore, it's sort of everything increases. You see, all the boxes are sort of higher up here than they were here. And if you go from control to the super gain, it also changes, or it doesn't really have to change between these 2. It's enough that there is a difference between 2 of them, right? Between 2 of the levels. That's the null hypothesis we test now, that all are equal, right? And it's enough that one of them deviates, then we should have a small p-value. However, the interaction term, diet combined with supplement, this is not significant at all. And this is also something we can sort of see from the plot here, because we will come back to it. What does it mean to have a significant interaction? It means that the picture you see in one panel changes sort of dramatically in some other panel. For instance, we have this tendency of dropping when you go from the first to the second to the third level. It gets smaller and smaller, right? And it's exactly the same in all 4 cases. If, for instance, this one had been opposite, so it was going from low to medium to high, then you would have probably had a significant interaction, because it means that the relation between the levels of one factor changes completely when you move to another level of the other factor. So that's an interaction for you. But in this case, it was not. But what about if we now run the summary here? So let's talk a little bit more about this interaction, because it's somehow difficult sometimes to interpret this interaction. So what happened now when we run the summary? We saw it earlier that now we test the null hypothesis that each of the effects are significant. And what does it mean to say it's significant? It means that the modification you go from the reference level, and in this case the diet, the reference is level 1, which is barley. If you jump from barley to oats, is there a significant effect? Is the response changing? Yes, it is. Right? If you go from barley to oats, it drops. It's negative, right? Minus 2.8. That's the main effect. And this is so all over the place, right? And the same if you go from barley to wheat. It's even more, right? Even more negative and even more significant. And the same for the supplement here. So actually for the main effects, this is just the same as if there was only one factor like we saw previously. What about this one then? This interaction here. We can see that it's not significant, but what if it had been significant? What does it actually mean to have a significant interaction? Well, first of all, notice there are only 6 interactions estimated. 6 interactions. And why is this? I wrote about it here. Because there are actually 12 combinations, right? But remember from the slides, when you do this contrast treatment parametrization, all these here are assumed to be 0. So they are, of course, not estimated. They are set to 0. So we only estimate the interactions that do not involve any of the reference level. Can you see that? This is interaction 1, 1, right? Involves the reference for both factors. And then 1, 2, 1, 3, and 1, 4 is set to 0. And also 2, 1, and 3, 1. So all the interactions were involving some of the 2 reference levels for factor alpha or beta are set to 0. And we only estimate those who are not including a reference level. And these are the 6 you see here, right? So of the 12 combinations, only 6 of them are estimated because the others are fixed at 0. So what if this p-value here had been super small? And we reject the null hypothesis. What is the null hypothesis? Well, the null hypothesis in that case would be this one, because this is level 2, right? Diet oats is the same as alpha 2. And supplement Agrimore is the same as beta 2. These are levels 2 for the 2 factors. So it means the null hypothesis that this interaction is 0. And if the p-value had been small, this had been rejected. So we say that, okay, this interaction is not 0. And what does it mean if we plug it into the to the equation? And for combinations of factor levels 2 for both factors, and look at only the expected response, then you take away the error term, right? Because it has 0 expectancy. So then it would look something like this. So notice what this interaction then is actually doing. It's modifying the main effects, right? It's sort of a modification of the main effects here. So in other words, we can say in general, if there is a significant interaction, the effect of one factor depends on the level of the other factor, right? There are 2 factors here. If there is an interaction, if there is a significant interaction, the effect of one factor depends on the level of the other factor. And it goes both ways. You can say that the effect of alpha depends on the levels of beta, or you can also say the effect of beta depends on the levels of alpha. Goes both ways. But since we don't have a significant interaction here, the p-values are not small, we can sort of say, okay, we don't reject the null hypothesis, and this is ignorable. Ignore this one here. Then we are actually left with a situation where The effects of alpha does not depend on the level of beta. It's the same regardless of the factor beta. And this is also what you see here, right, in the plot. The effect of alpha is how when you move from barley to oats to wheat, right? Barley to oats to wheat. This is the same regardless of which panel you are in. Barley to oats, it drops approximately the same in all 4 cases. So this fits nicely with having no interaction. The picture is the same. Okay, you will see some exercises where we have a significant interaction effect. Let me just show you some nice code here for plotting effects. This is this is an alternative to the ggplotting that I did here. So I use a package called effects here. And let's plot the main effect of diet. How does it look like? This is the plot that we get. And here we clearly now see that there is a main effect of diet going from barley to oats to wheat. This is sort of the fitted values, right? So we can clearly see, and these lines have been added. It's actually only the dots, right? This line is just for sort of a trend line. Yeah, it's a little. I'm not sure I like this because it gives you an impression of something continuous. It's not, right? It's either barley or oats or wheat. There is nothing in between. But okay, we can see that it and these error bars indicate that when they don't overlap, you can for sure say that this must be a significant effect. We can do the same for the supplement, main effect of supplement. And here we see it again. Control is here, and then it's a big increase to Agrimore. The change to this one is perhaps not so big, but okay. And then here again. But there is a significant effect. There is some deviations, right? For some of them are. This one is surely different from this one. And we can also plot all effects together. And this is an alternative to this ggplot that I made. And you can see it's now, instead of having 3 levels on the x-axis and 4 panels, this is reversed. We have 4 levels on the x-axis and 3 panels. But it's the same image, sort of, right? And we can clearly see that there is no interaction because the picture we see here is very much like the picture we see here is very much like the picture we see here. So if there was an interaction, the shape you can see of these curves should change dramatically in one of the panels, but it doesn't. So we can of course also look at diagnostic plots like we have done before. This is no difference if you have 2 factors compared to if you had 1 factor. So let me just make the common diagnostic plots that we usually do. Right? We look at the residuals and see if there is a trend, if there is a constant variance. Looks fine. And also if there is sort of normal distributed. Yeah, this is also quite fine. And we can also do pairwise testing like we did when we had a single factor. But of course, this can now become horrible if you have a lot of levels. And now I try to do it for the interaction, which has quite many levels, right? And this is, so let me just run it and we print it and we can even plot it. And here you can see this can quickly become a mess, of course, when you have too many levels to compare, right? Because here we have, yeah, it's like 6 interaction terms and all the pairs, right? Between them again is, yeah. So it becomes a mess. So this was not a good idea, I would say, but we can, what we typically would do then, we saw above that this interaction term was not significant, so we should actually refit our model, and that's what we do here now. So let me refit the model without the interaction now, right? Because we found immediately from the first F test really that there was no significant interaction here, and then we should actually throw it away immediately. So I didn't do that, but that was just to show you something. But in real life, if you have a non-significant interaction, throw it away immediately. It just complicates things. You only include it if it is necessary. So let me refit the model here. Yeah, we can make the ANOVA again. Doesn't change much because these two are highly significant already, and they become even more so now, I suppose. The same for the summary here, the main effects, right? It's much smaller and nicer now. Yeah, this was not significant, right? And this was the super gain was not significantly different from the control level, right? Because that's how we compare now against the reference level. So, but still we can make the pairwise test. That's more reasonable now. And now I test only the diet here, right? And then we can print the diet results. And then we see here that there is a significant difference between barley and oats because the confidence interval does not cover zero. Both lower and upper bound is positive. The same here and the same here. All the three levels are significantly different from each other. And now you can do the same for the supplement and see if you get the same results as we saw above. So a few words about errors and power at the end, even if this was a very long lecture. So we make hypothesis tests, right, in all kinds of variants. And each time we do so, we can make two types of errors. The type 1 error by rejecting null hypothesis when it is actually true, or the type 2 error retaining the null hypothesis when it is actually false. The probability of type 1 error we call alpha, and the probability of type 2 error we call beta here now. And then what is typical is that we are very much concerned about this alpha, the probability of making type 1 error. And that is also why we want this to be super low, actually. So each time we look at the p-values, we say that if this is below alpha, we reject the null hypothesis at this level of significance, right? 5% level in this case, then if 0.05. So that's why we are sort of strict, right? We don't reject null hypothesis until we are sort of pretty sure, right? We don't want to make this error. How about this other one here? Let's put up this 2x2 table, because null hypothesis is either false or true, right? This is not known. We don't know which one of these they are, but we either reject or we retain. And of course, if we reject and it is true, we make this error, right? So this is the probability of doing this error, while this is the probability of doing this error. And if we are here or here, we are happy. The point is, in this table, both columns sums to 1, as you can see, beta and 1 minus beta, alpha and 1 minus alpha, but not the rows. So it is, in theory, possible to have this one very low and at the same time have this one very high, or opposite. So so this is the alpha is sort of what we decide by deciding this rejection threshold. But at the same time, this inflicts this beta, sadly. We fix alpha, but how can we control the beta? Yeah, that's a different story. And that's what we are going to see a little bit now. If we focus on the 1 minus beta, then it doesn't really matter. Right? If you say that this should be low, it's the same as saying that this should be large, right? This should be small, this is large, because as you can see, they sum to 1. And this is the power of the test, this one, 1 minus beta. The ability to actually detect an effect when it is there. And that should be big, right? The probability of this one. We would like this to be big. And a big power, powerful test, as we say. So the power of a test is the ability to detect an effect when it is actually there, right? Rejecting null hypothesis when the null hypothesis is indeed false. So we do a sort of correct rejection. And the probability of this is 1 minus beta. This is power in statistics. So we would like to have this as big as possible. Sadly, this alpha and beta are in general not unrelated. So the smaller we choose the alpha, safeguarding against the type 1 error, the larger this one tends to get. And that means a lower power, right? And this follows due to the randomness in the data, that you cannot sort of separate this entirely from each other. They are not. It's not like a formula for how they are related, but we can do what we call power calculations. We can fix an alpha, and then we, under some assumptions, we can see how much data or how much data quality is needed to detect an effect with a certain probability, 1 minus beta. And this can be sometimes very valuable, right? If you're going to make some experiment, you fix the alpha, let's say at 5%, 0.05. This is your tolerance for type 1 error, right? How much data do I need with this alpha to get a power of, let's say, 90%, right? 0.9 here. And this is possible to make some calculations, not without assumptions, but it's still of some use, right? Because it indicates to you how much data do I need to collect before I can expect this to happen. And if that turns out to be sort of impossible, then you should perhaps think in a different direction, right? So making these power calculations can be useful prior to starting an experiment, for instance. In the exercises, you will do this by using this Shiny app here. So I will not actually do it here now. I leave it to you to try it on your own, and you can ask for help, and you will get some solution for this afterwards. Okay.